Right, thank you very much. I'm Dr. Cho from the UK Centre for Ecology and Hydrology. I'm in the Environmental Data Science group in Lancaster. Just before I start my talk, we are currently organising data science in Afghanistan. Spring school for March next year. For March next year, so chat to me if you want more information. Yeah, we're also advertising for some vacancies and PhD positions as well. So now back to the talk. Yeah, today I'm going to talk about this work on state tagging for improved contextual understanding of environmental data. We published a paper on how to use this conceptual framework for QA/QC of environmental data. A while back. Hello? So, yeah. Yeah, so we published this paper on QA/QC of environmental data a few years ago now, but just wanted to introduce the framework again and also talk about some of the extensions that we can do within this framework. So it is a clustering-based framework that is supposed to improve the QA of environmental data. It's very efficient and is virtually applicable to any point-based time series data. It can be extended to other types of data as well. It can give greater confidence for users to use third-party data and encourage collaborative research. Cool. As all of us know, increasingly, we are facing a big data challenge. We are asked to solve bigger problems in environmental science. It's more often now that we will use some data that we didn't collect ourselves, some big data stores, or using integrating multiple data sources. So we need to find a way to QA/QC the data that we use, especially those that are not very popular or the kind of big data sets that are out there. Maybe specifically need for you to integrate them. So we want to have a general tool to give users some ideas about the data quality, and that is also informed by the other data that's going around at the same time. So before this framework, most quality checks are done by range checks. So yeah, whether it's about certain range or below certain range, whether it makes sense or not. But we actually have a lot of other data that's been collected at the same time that we can use to tell whether it's falling within the right range at the right time. So we introduced this idea of state to recognize that the acceptable right range can be different in different times or different situations, and then we can overlay the prediction that is acceptable in this state on the data to give the user better confidence on the data. We have the same problem with some of the shapes again, using the TV screen. Basically, we would have a data frame with time steps and state data. Then we will use a unsupervised machine learning method. Here we use k-means that can be swapped to any other method. It could even be an AI model, but we use that data to learn the data, to segregate the data into different arbitrary states. And then we could append this this state number to the environmental data we're going to use, and then make some prediction intervals around the data. So this is a very general overview of it. Hopefully, I show a couple of examples to make it clear to you. So skip this slide. So this is a screenshot of an app with how this method can be implemented. So what you have here is some time series data. So this is, for example, we have data from a weather station. Then let's say I use several data for different types of data like solar radiation, temperature, rainfall, and so on. Then I cluster the data into several different states, and then I can color code each data points at bigger state. And then I can say, okay, state 1 days would have this kind of range from observed data. State 2 days will have a different one stage. Then we can overlay this envelope of prediction intervals on data to give the user better confidence. So at the bottom right, this is TOCA, so it's chlorophyll data from the lake monitoring station. If we're just doing rain checks, we probably have a very wide envelope of acceptable values, but here we are basically we count for the changes of the lake condition from other data available in the lake boil. It could be a weather station data, it could be weather forecast data as well. But we avoid using rain checks, and we avoid using seasonality as well, because for climate change, seasonality is not always the most useful tool. It's very hard, still very rigid criteria. This is a purely data-driven criteria. You can check the data. This is an example from an environmental change network. So it's a long time series of weather conditions. So these sites have data from the collocated measurements of many different calculators like soil chemistry, morphcams, whether they're all measured at the same site. So here, I'm showing you that it's the 4 types of weather data I use for defining the states. And you can see that they have certain characteristics. For example, on the second one, you can see the state 1 is just high solar radiation. So there are some, this data-driven method still give you some characteristics of physical meaning. And then you can overlay these values on the morphcam values, and you would get 95% prediction intervals on data. Similarly, I mentioned this other lake example that you can use. Again, these are data that are automatically fed by a buoy. You can define certain state values. So we're considering water temperature, wind speed, and solar radiation on the boil to define the states. And then you can overlay, use that to give state specific prediction intervals on the chemistry data. So here's chlorophyll, dissolved silicon, and nitrate. Yep. I said a little bit about extending this to a spatial example. So this is an app we have developed for the predatory bird monitoring scheme. So we receive bird samples from all across the UK. It's a citizen science project, and then we do biopsy on the birds to see look at their chemical exposure levels. But we can use it to this state taking concept as well. We can use, for example, lat long or altitude, distance to goals, take off physical variables to define the state where we find the birds, rather than using rigid grouping strategies, for example, like just regional in the country, thing to give us some more flexibility to understand the data. The one great advantage of this method is that it's not limited to the kind of variables that we collect. For example, I said you can use weather data, but maybe in some of the data there's a lag effect. For example, fish characteristic in the lake, maybe it's not affected by the temperature today, but maybe it's affected by temperature a month ago, and so on. So actually, you can build a lot of different features from the data, and all of that would be accepted within this conceptual framework that can be used to give you additional variables for defining the states. Then currently, we have just submitted a bit to look at adaptive sampling on very high frequency water quality data monitoring. These samplers are measuring super high frequency, but there are issues if they're always monitoring at very high kind of 15-minute or over interval So we can use this framework using the weather stations or other data to define certain states to trigger an event state that you would start monitoring at high frequency. So you can use the readings on the sensor, you can use other sensors in the facility, or even models such as weather forecasts. So I'll skip the summary, but these some of the apps are available for trying. I'll use this slide and take some questions.
Thank you. Does anyone have any questions? Any time for 2 questions?
Hi, I have a question about the method you use, the K clustering. How did you evaluate the accuracy of this method? Because I know there are multiple clustering methods, and after clustering the data, how did you find out the difference between each clustering? And how did you give them their features or labels of this clustering group?
So first, the framework is not limited to k-means clustering. You can use other clustering methodologies. But here we kind of, the main criteria we look at is the elbow curve, so we avoid overfitting the data. That's how we define the optimal number of clusters and not overfitting the data. In terms of labeling, we didn't use any labeling, so it's basically the state is basically assigning a flag that you can the data, and then the interpretation of the state or the flag is entirely up to environmental scientists. It's a way for it's a first pass to look into the data. We're not enforcing any labels on the data.
So what the label means is that how do you find out their features? Because if they are different, they are divided into different clusterings. They might have different features and different attributes. So can you find out the features and attributes based on the clustering?
No.
So
it's a way to look at the data. So we don't. It's not a semantic segregation type of word. At least at the moment.
Okay, thank you.
Okay, thank you very much, Michael. I'd like to invite our next speaker.